Hello my friends and welcome back to the You Can Do TV channel. At the BAM Wind Turbine Project, precast concrete panels are carefully positioned to form the gravity-based foundations. Cranes lift each panel into precise alignment, ensuring stability for the massive offshore structures. Panels are braced and secured as work progresses, maintaining exact tolerances for load distribution. This method allows for efficient assembly in challenging marine conditions, providing a durable and reliable base for the turbines. The process highlights meticulous engineering and coordination, essential for long-term offshore wind energy performance. At Westad Harbor, the construction of the new quay relied on the production of two massive concrete caissons, each weighing approximately 500 tons. These enormous, prefabricated structures were designed to form a robust and stable foundation capable of withstanding harsh marine conditions, heavy loads, and continuous operational demands. To achieve the highest quality, the caissons were cast in a controlled production environment, where temperature, humidity, and material consistency could be carefully managed. High-strength concrete was used in combination with dense steel reinforcement to ensure both durability and structural integrity. The reinforcement cages were precisely assembled to meet strict engineering requirements, providing resistance against cracking, impact forces, and long-term fatigue caused by waves and vessel movements. Throughout the casting process, rigorous quality control measures were applied, including material testing and dimensional inspections, to guarantee accuracy and reliability. Once casting was completed, the caissons underwent a curing period that allowed the concrete to reach its full strength. Special attention was given to surface finishing and sealing to protect the structures from seawater penetration, corrosion, and freeze-thaw cycles common in Nordic coastal environments. After preparation, each caisson was carefully readied for transport, a complex operation that required detailed planning due to their immense size and weight. The installation phase involved precise positioning at the harbor site, using specialized marine equipment to place the caissons accurately on the prepared seabed. When installed, they formed a stable quay structure that significantly enhanced Ystad Harbor's capacity and safety. These caissons now play a vital role in supporting maritime operations, ensuring long-term performance, resilience, and operational efficiency for the harbor's future development. The Hanstholm caisson is a monumental offshore structure designed for Denmark's coastal protection. The caisson incorporates 850 tons of reinforcement steel, carefully fabricated and positioned within the structure to provide maximum strength. Beneath the bottom slab, 810 square meters of teeth-shaped steel plates are installed to enhance stability and anchoring on the seabed. The bottom slab, measuring 40 by 23 meters and 0.7 meters thick, required the movement of a 150-ton steel cage over a distance of 60 meters during assembly. The walls of the caisson, with heights reaching 16.3 to 16.5 meters, were cast in 16 separate phases, totaling 704 square meters of concrete. Precision casting techniques and quality-controlled curing ensured the structural integrity and durability of the massive unit. The deck installation involved lifting 8 concrete slabs of 85 tons each using a floating crane. To facilitate easier access during lifting and assembly, the barge was rotated strategically. Once completed, The entire caisson weighs approximately 900 tons. For final deployment, the caisson was carefully released from the submersible barge and towed to its designated location off Hanstholm, Denmark. Throughout the process, all structural components were monitored for dimensional accuracy, concrete strength, and reinforcement placement, ensuring the caisson met stringent offshore engineering standards. This combination of heavy lifting operations, phased casting, and precise assembly demonstrates advanced offshore construction techniques for large-scale maritime infrastructure. Hinckley Point C represents a landmark in nuclear construction, featuring two cutting-edge European pressurized reactors designed to generate 3.2 gigawatts of low-carbon electricity, enough to supply 6 million homes and cover 7% of the UK's electricity demand. The construction site spans 175 hectares, making it one of the largest and most complex civil engineering projects in the country. Each day, nearly 10,000 engineers, technicians, and skilled workers collaborate across multiple disciplines, from structural and mechanical installations to electrical systems and safety-critical components. Advanced construction techniques are applied throughout, including precision concrete pouring for reactor basements, high-tolerance assembly of nuclear-grade steel structures, and integration of reinforced containment systems. The project also emphasizes modular construction, allowing large prefabricated units to be assembled on-site with extreme precision. Hinckley Point C is not only a technical achievement but also a model for sustainable energy infrastructure. Every stage, from excavation and civil works to reactor installation, is meticulously planned and executed, ensuring compliance with stringent safety and quality standards. This monumental project showcases modern nuclear engineering, large-scale project management, and innovative construction methods aimed at providing safe, reliable, and low-carbon energy for decades to come. Concrete working platforms have been a maintenance-free, integrated part of offshore wind turbine foundations for over a decade. Designed with high-strength concrete, these platforms withstand wave impacts while providing safe working conditions, offering a cost-effective alternative to traditional steel platforms. The concept was developed by Arslef Biz in 2007, and since then over 1,000 platforms have been deployed worldwide. Production takes place in the company's certified factory in Świnoujście, Poland, close to suppliers of concrete and reinforcement steel, reducing transportation and logistical risks. Aggregates are mixed with cement and water in a concrete plant, and prefabricated rebar cages are placed in project-specific steel formworks, designed for stationary or mobile use. These formworks ensure correct dimensions and durability. All cast-in items and rebar cages are quality checked, while a third-party laboratory monitors concrete strength using temperature measurements and maturity systems. Once concrete reaches sufficient strength, formworks are stripped and platform accessories are installed. These include railings, davit cranes, electrical equipment, access staircases, and life-saving equipment, all manufactured and tested to meet client specifications. Each davit crane undergoes a static load test to verify performance. Completed platforms are transported using RTG shipyard trailers and loaded onto barges or coasters by floating cranes. Typical deliveries range from 15 to 25 platforms per shipment, depending on size and client schedule. From the first delivery for Horns Rev 2 to recent projects in the North Sea, UK, Germany, Denmark, and the USA, Arslef Biz has produced and installed 643 patented concrete working platforms, ensuring safe, durable, and cost-efficient solutions for the offshore wind industry. At the Nissum-Bredning offshore wind farm, 4 massive concrete transition pieces, each weighing 200 tons, are being produced for Siemens Gamesa Renewable Energy. Each transition piece incorporates 500 kilograms of reinforcement steel per cubic meter of concrete, ensuring exceptional structural strength and durability to withstand harsh offshore conditions. The production process involves carefully assembling steel reinforcement cages, which are precisely positioned to maintain design tolerances. High-performance concrete is then cast into the molds, totaling 450 cubic meters per transition piece. Advanced curing techniques ensure uniform strength development and long-term durability. Once cured, the transition pieces are prepared for installation atop 3-leg jacket foundations. These jackets are securely connected to piles set on a radius of 10.6 meters, providing stability for the offshore turbines. Specialized lifting and transport equipment is used to move each 200-ton piece from the casting yard to the installation vessels, ensuring safe handling throughout the process. This rigorous approach guarantees that each transition piece meets the demanding technical standards required for offshore wind energy, supporting reliable turbine operation for decades. At Fort Boyard, a monumental engineering effort is underway. Massive protective structures are being constructed onshore at the port of Nantes-Saint-Nazaire, crafted as single, monolithic blocks to ensure precision, strength, and durability. Each piece faithfully mirrors the granite of the fort, blending seamlessly with its historic environment. These colossal elements are designed to withstand the relentless force of the sea for the next century. Advanced handling systems allow safe flotation and transport, with the first blocks scheduled to be towed to La Rochelle in 2026, positioning them at the foot of Fort Boyard, followed by additional sections in 2027. By building on land, engineers achieve unparalleled accuracy while minimizing the complexities of offshore operations. This project combines cutting-edge logistics, meticulous engineering, and visionary planning to protect one of France's most iconic maritime landmarks. The Vladivostok cable-stayed bridge, spanning the eastern Bosphorus Strait to Russky Island, features a record-breaking channel span of 104 meters and pylons rising 324 meters above water. Construction began in September 2008 and faced extreme environmental challenges, including storms, fog, high winds up to 36 meters per second, winter temperatures below -30 degrees Celsius, and ice up to 70 centimeters thick. Two production facilities on the Nakhimov Peninsula and Russky Island ensured continuous supply of materials. These included rebar and welding workshops, steel span module assembly buildings, laboratories, mechanical workshops, and 4 high-capacity concrete batching plants. Over 300 meters of rail tracks and raised ramps facilitated delivery of steel structures and concrete, while berths and aggregate storage on the island supported uninterrupted operations. Construction employed 320 specialized machines, including 40 and 20-ton tower cranes rising 340 meters for pylon erection, and a 350-ton Liebherr crawler crane for steel deck installation. Viaducts, over 900 meters in length, provide approach spans, with piers up to 30 meters high and box-shaped deck members with inclined webs attached to cast-in-place concrete slabs. Pylon foundations utilized 120 drilled piles per pylon, some up to 77 meters deep. Self-compacting B35 concrete was used for pier and pylon grillage, with strain gauges embedded to monitor structural health. Pylon bodies were cast with B60 concrete using custom self-lifting formwork, 7 tiers high, reducing erection time by 1.5x. The steel navigation span stiffening girder, over 248 meters long, consists of 103 main panels and 2 transition panels, pre-assembled at production facilities and lifted to 70 meters. Each welded joint underwent ultrasonic testing for quality assurance. The bridge employs an advanced stay cable system, 720 tons in total, with 13 to 85 corrosion-protected strands per cable enclosed in high-density polyethylene jackets. Compact cable configuration reduces wind load by 25 to 30%, optimizing material use. Decorative jackets feature helical grooves to mitigate vibrations. The project demonstrates integrated engineering, construction logistics, and advanced materials technology, ensuring structural durability, safety, and longevity. Once complete, the bridge will become a landmark for Vladivostok, combining world-record span engineering with cutting-edge technical solutions. The Vals-Mont Blanc Viaduct on the A27 highway features 2 carriageways, each with 5 spans, totaling 180 meters in length. Construction occurs in 2 phases, with the first phase covering 2 spans plus a 5th, and the second completing the remainder. The deck has a gull wing profile with variable thickness between 1.5 and 3 meters, supported on piers up to 27 meters high, built using climbing formwork. The carriageway widths are 12.40 meters for the left and 15.90 meters for the right. Tecozam's Portal formwork system enabled precise adaptation to the complex geometry, including steep transverse and longitudinal slopes and variable deck thickness. Concrete placement at height required handling sections weighing 73 tons per linear meter, ensuring both structural integrity and construction efficiency. This innovative method guarantees safety, quality, and timely completion. The Viaduct Os Portos, part of the high-speed rail Madrid-Galicia, spans 246 meters, with segregated tracks supported by hollow rectangular piers up to 40 meters high. Construction begins with precise pier placement, ensuring vertical alignment and load-bearing stability. The concrete box girder deck is cast using advanced formwork systems. VGT 100 deck formwork provides exact shaping for the concrete, while TC 4000 heavy-duty shoring towers support the spans during curing. Long spans up to 24 meters are stabilized with County Route 24 heavy-duty trusses, distributing loads and preventing deflection. Reinforcement cages are pre-assembled and placed in the formwork before casting, and concrete is poured in controlled segments to ensure uniform strength. After curing, formwork is stripped and piers and decks are checked for alignment and quality. This process integrates specialized formwork, heavy-duty shoring, and precision engineering, ensuring safety, efficiency, and long-term durability of the viaduct for high-speed rail operations. Poles and Concrete Limited manufactures pre-stressed high-strength concrete piles, also known as spun pre-stressed concrete piles, using advanced global technology. These circular, pre-tensioned piles are widely used internationally, particularly in Germany, Japan, Malaysia, Indonesia, Taiwan, Korea, and China. In Bangladesh, the company produces both spun pre-stressed boards and piles, leveraging extensive experience in high-quality, pre-tensioned concrete products. PHC piles are circular in cross-section, ranging from 200 mm to 700 mm in diameter, with standard lengths of 6 to 15 meters per segment. They can be joined in various configurations with steel end plates for splicing according to design requirements. Production follows ISO standards and Japanese norms, ensuring consistent quality. The piles are manufactured using centrifugal compaction and steam curing, producing uniform, high-strength concrete. Poles and Concrete Limited maintains a dedicated laboratory to test raw materials and finished products, with additional verification through third-party CRT testing. A ready-mix concrete plant ensures high-quality concrete supply for projects. For installation, PHC piles are driven using hydraulic static pile driving machines, allowing rapid and efficient piling. The company can drive up to 30 piles per day, significantly reducing project timelines while maintaining strict quality standards. This process ensures reliable, durable foundations for At the Gemini Offshore Wind Park, each monopile is fabricated with precision to fit its designated location. Two cold-bent steel plates form a single section, 5 meters in diameter, with cable openings and tapered attachment flanges added for structural and functional requirements. After approval of the sections, the monopiles are fully assembled and welded, resulting in units weighing up to 700 tons and measuring 59 to 73 meters in length. Completed monopiles are carefully lifted onto barges for transport to Vlissingen for intermediate storage. At Smulders in Antwerp, the steel hulls of the transition pieces are lifted into production halls, where connection points for ladders, platforms, and boat landings are installed. The structures are then coated for corrosion protection and undergo a final inspection before shipping to the harbor in Eemshaven. Simultaneously, in a separate hall, two offshore high-voltage substations are fabricated, incorporating heavy steel components, cable connections, and safety access systems. This process integrates precision engineering, welding, protective coating, and quality assurance, ensuring each component meets strict offshore specifications for durability, stability, and seamless installation at sea. At the LNG process plant in Northern Australia, large-diameter steel tube piles are being driven to create strong, durable foundations. Each pile extends up to 12.5 meters, designed to support the heavy loads of LNG processing equipment while ensuring long-term stability in challenging soil conditions. Construction starts with precise surveying and positioning, ensuring every pile meets exact design tolerances. Specialized pile driving rigs, equipped with heavy hammers, drive the steel tubes deep into the ground. Temporary guides maintain vertical alignment, while real-time monitoring of penetration depth, blow count, and position confirms each pile reaches its required capacity. Where necessary, pre-drilling or vibratory assistance enhances efficiency and reduces soil disruption. Once installed, pile tops are cut and leveled, ready to integrate with concrete pile caps and the plant's structural framework. The installation of the Gemini offshore wind park turbines involves a carefully coordinated technical process. Towers, nacelles, and 65-meter-long turbine blades are loaded onto installation vessels in Esbjerg. Each Aeolus trip carries 6 complete sets of towers, nacelles, and blades, while the Pacific Osprey transports 8 sets. The turbine hub sits 89 meters above sea level, requiring precise handling. Installation vessels sail approximately 12 hours to the Gemini wind farm. Once jacked up, the vessel's crane is ready to lift the complete top section. On the transition piece, riggers prepare the connection points for secure assembly. Special lifting tools ensure fast and safe operations under full control. Guided by riggers positioned atop the towers, the crane operator maneuvers each nacelle into its exact position. Following this, the 3 turbine blades are individually secured and attached using the lifting tool, allowing for smooth rotation and alignment. The turbines are designed to operate continuously, even in strong winds, up to force 11, above which they automatically shut down for safety. By mid-2017, all 150 turbines in the Gemini wind park are expected to be fully operational, generating clean, reliable energy efficiently. At LM Wind Power, every blade begins with a custom design, crafted for maximum energy output and long-term reliability. Using advanced tools and decades of expertise, each blade undergoes rigorous static and fatigue tests, along with lightning strike and aerodynamic trials in the wind tunnel. During production, glass fiber layers are meticulously laid, while balsa wood panels or PET foam add strength and stability. Carbon fiber is incorporated in longer blades for enhanced stiffness. Resin infusion forms a strong composite laminate, and the shear web is glued between the 2 shells. Finally, the shells are joined, and the finishing process ensures perfect quality. Each blade is now ready to power homes worldwide with clean, reliable, and sustainable wind energy. The Octocong is one of the world's largest vibratory driver extractor assemblies, engineered by American Pile Driving Equipment for the monumental Hong Kong-Zhuhai-Macau Bridge project, conceived to meet unprecedented foundation challenges. Instead of traditional pile driving methods, which would have taken years, the Octocong combines 8 synchronized vibratory pile drivers powered by 8 Caterpillar 1 200 HP engines to deliver immense force needed to drive 120 steel piles up to 72 feet in diameter and more than 130 feet long into the seabed. The innovative system reduced the construction schedule to under 7 months and represents a significant leap forward in sea-bound construction technology. During operation, the vibratory drivers, mechanically and hydraulically linked, generate controlled vertical oscillations that reduce soil resistance, allowing the enormous piles to penetrate efficiently. Precision synchronization is critical, as the system must maintain equal force across all hammers to drive the piles straight and to depth. The complete octagon setup shows the crane-mounted assembly lifted into position, the massive pile being guided into the seabed, and the synchronized vibratory drivers at work, demonstrating both the scale and power of this groundbreaking equipment on one of the most ambitious infrastructure projects in the world. At the Blythe Offshore Demonstrator Wind Farm, Boskalis Subsea undertakes the critical operation of shore landing the export cable. The project involves the simultaneous laying and burying of a 6.5 kilometers 66 kV export cable, connecting the offshore turbines to the onshore grid. The operation takes place off Cambois, United Kingdom, using the CLV Endurance, a cable-laying vessel positioned on anchors 450 meters offshore. The vessel carefully maneuvers while pulling the HD3 plow towards the beach, which precisely embeds the cable into the seabed. During the cable pull-in, the plow simultaneously lays the cable and ensures it is securely buried, providing protection against environmental forces and human activities. This method reduces the risk of cable exposure and ensures long-term reliability of the wind farm's power transmission. The client, EDF Energy Renewables, relies on this advanced subsea installation to connect renewable energy from the turbines to the national grid efficiently. The operation demonstrates precise engineering, careful coordination, and the use of specialized equipment. The Gemini offshore wind park cable installation involves precise engineering and careful sequencing. The process begins with connecting the export cable to the land high voltage station in Eemshaven, ensuring secure and reliable power transfer. In shallow waters and tidal flats, the cable is carefully laid along the seabed, with Nessie 2 performing burial operations to protect it from external impacts and maritime traffic. Where existing cables are present, advanced techniques allow the new cable to be laid underneath without disruption, including a 550-meter HDD horizontal directional drilling section to cross sensitive areas. In deeper waters, the cable-laying vessel Nexus handles the export cable with precision, maintaining tension and alignment. Simultaneously, Nexus lays 150 infield cables, connecting individual turbines to the offshore substation. The entire operation emphasizes accuracy, protection, and reliability, ensuring long-term performance of the offshore wind park's electrical infrastructure. The Calais Port 2015 project is one of the most significant French infrastructure undertakings of the decade, creating over 4.5 kilometers of dikes, including a main dike exceeding 3 kilometers. This ambitious marine construction presented major technical challenges, requiring robust solutions against waves and storms. At the core of the project are the X-blocks, massive prefabricated concrete elements patented by DMC, forming the first line of defense of the dike. To ensure quality and precision, an automated X-block production plant was built on-site by APS, part of the French SME CBO group. Aggregates are sorted by size and transported to a concrete batching plant, where cement and water are mixed to produce high-quality concrete. Fresh concrete samples are analyzed in the on-site laboratory to guarantee strength, durability, and traceability. Once ready, the concrete is poured into molds of varying sizes, producing 28 to 40 X blocks daily, with volumes ranging from 4 to 14 cubic meters per block. After casting, molds are conveyed to drying lines and cleaned for immediate reuse. Finished X blocks are moved to temporary storage, then to a final storage area holding over 1/600 units. For precise placement, each block is equipped with a gyroscopic cell, PIB, and acoustic camera, providing real-time information on roll, pitch, and heading. The position and interlocking of each block are recorded and validated by DMC, ensuring stability and durability. A total of 16,000 X blocks will secure the new Calais port dike, safeguarding maritime traffic and visitors for decades. The production of Cubipod's wave breakers for the Hanstholm harbor expansion in Denmark begins with the preparation of special high-density concrete, exceeding 2,700 kilograms per cubic meter. This ensures that each unit can withstand the extreme forces of the North Sea. Concrete is carefully mixed to achieve the required density and uniformity, then poured into precisely engineered molds. These molds are designed to form the interlocking shape of the cubipod, which allows the units to dissipate wave energy effectively when deployed. Each element undergoes controlled curing and quality checks, verifying its weight, dimensions, and structural integrity. The project required 400 units of 15 tons and 200 units of 30 tons, demonstrating the massive scale of production. After curing, the elements are transported onto sea barges. Each delivery carries up to 600 units, totaling 42,000 tons of material transported to the harbor site. The Synchrolift elevator test tower in Atlanta, Georgia, stands as a striking example of modern concrete construction and engineering precision, rising to approximately 420 feet as part of the company's new North American headquarters at the Battery, Atlanta. Its central core was constructed using an advanced slip-form technique, a continuous concrete pouring method that allowed the tower to climb vertically without conventional formwork resets. Slip-form construction is widely used in Europe, but remains relatively rare in the United States, making this project notable for its efficiency and engineering ambition. The method creates the skeleton of the structure as a continuous monolithic wall, ensuring both strength and durability for the tower's reinforced concrete core. The tower will house 18 elevator test shafts, enabling trials of cutting-edge technologies including high-speed elevators, dual cabin systems, and next-generation mechanisms as part of the Innovation and Qualification Center. Once complete, the facility will serve as a global testing hub and a visible symbol of innovation in vertical transportation. Overall, the slip-form process not only accelerated construction but also demonstrated exceptional coordination, quality control, and technical expertise on one of the tallest elevator test structures in the Western Hemisphere. Bolted column connections offer a faster, safer, and more efficient way to assemble structural columns. Perfect for structural designers, precasters, and contractors, this system simplifies the construction workflow. Designers benefit from easy planning with Revit and AutoCAD components, while precasters enjoy smooth installation into molds, and contractors gain speed during erection. A column can be securely installed in just 10 minutes using a simple two-part system: column shoes cast into the precast column, and anchor bolts positioned in the foundation with practical templates. Unlike traditional methods, no temporary bracing is required, and the connection becomes rigid as soon as the nuts are tightened. This approach saves crane time, reduces manpower, and works efficiently even in seismic zones, making it a reliable, modern solution for rapid and safe column installation. At Nosco Shipyard in Quang Ninh, Vietnam, vessel docking and repair operations are carried out with advanced infrastructure and systematic processes to ensure safety, quality, and efficiency. The shipyard is equipped with one of the largest Synchrolift systems in Southeast Asia, capable of lifting vessels up to 82,000 dwt quickly from the water and transferring them to dedicated repair platforms. This modern lifting system dramatically reduces docking time and turnaround, allowing up to 7 to 8 ships to be serviced simultaneously. The process begins when a vessel arrives at the yard and is guided into position by skilled marine pilots. The Synchrolift then raises the ship safely out of the water in approximately 45 minutes, transferring it to a dry berth, where repair and maintenance work can begin. Once docked, the repair workflow follows a structured sequence. Specialized teams start with initial inspection and damage assessment, identifying hull wear, structural issues, or equipment needs. In well-equipped workshops, technicians perform steel renewal, hull blasting, and protective coating applications, often using hydroblasting robots and ultra-high-pressure water jetting to prepare surfaces. Next, mechanical and electrical systems are addressed. The shipyard's facilities include engine overhaul, propulsion system repair, and auxiliary machinery servicing, which may involve precision machining, testing, and load verification. Propeller and rudder repairs restore critical steering and propulsion performance. Throughout the repair process, quality assurance is maintained under international standards, with inspections conducted at each stage to confirm compliance with safety regulations and classification society requirements. When repairs are completed, the vessel is lowered back into the water via the Synchrolift and moved to the departure berth. By integrating advanced machinery, skilled engineering teams, and streamlined procedures, Nosco Shipyard delivers reliable docking and repair solutions that support global maritime operations with fast turnaround times, rigorous safety, and high technical standards. The prefabrication and transfer of caissons for the Breakwater at Nador West Medport represent a key phase in the development of this strategic maritime hub in northeastern Morocco. Located in the areas of Yazanain, Bouillafar, and the Reef region of Nador, the project is designed to provide robust coastal protection and support large-scale port operations. The caissons used for the Breakwater are massive reinforced concrete structures, prefabricated in a controlled casting yard to ensure high quality, dimensional accuracy, and long-term durability. Each caisson is constructed using high-performance concrete and dense steel reinforcement to withstand aggressive marine conditions, wave impact, and seismic effects. During prefabrication, strict quality control procedures are applied, including concrete testing, reinforcement inspection, and curing monitoring. Once completed, the caissons are prepared for transfer by carefully controlling buoyancy and stability. They are floated out from the casting basin and transported by tugboats to their designated installation positions along the breakwater alignment. This transfer operation requires precise marine coordination, favorable weather conditions, and continuous monitoring to ensure safety and accuracy. After positioning, the caissons are gradually ballasted and placed on a pre-leveled seabed foundation. They are then filled with granular materials to achieve final stability. This caisson breakwater system, dig caissons, provides excellent resistance to waves while optimizing construction time, making it a reliable and efficient solution for the Nador West Med port infrastructure. A steel bar manufacturing plant is a specialized industrial facility dedicated to producing high-quality steel bars for construction, infrastructure, and industrial applications. The production process begins with steel billets, which are produced from iron ore in a blast furnace, depending on the steelmaking route. These billets are carefully inspected for chemical composition and surface quality before entering the rolling process. After reaching the desired temperature, the billets are fed into a hot rolling mill, which typically consists of multiple stands with grooved rolls. Through successive passes, the billet is gradually reduced in size to the required bar diameter or profile. During hot rolling, the steel undergoes mechanical deformation, which refines the internal grain structure, enhancing the strength and toughness of the bars. Once the bars exit the hot rolling mill, they pass through a controlled cooling system, often using water sprays or air cooling, to stabilize the microstructure, reduce residual stresses, and improve mechanical properties. After rolling and cooling, the bars undergo rigorous quality control. Bars meeting quality requirements are then cut to length, bundled, and labeled for delivery. From raw billets to finished steel bars, this process emphasizes mechanical optimization, quality assurance, and material reliability, delivering durable steel products for global construction and industrial projects. At Slough Metalworks, DDS Demolition executes controlled structural demolition, including metal frameworks and industrial buildings. Licensed asbestos removal is conducted within secure enclosures, ensuring full containment and regulatory compliance. The team manages enclosure erection and dismantling with strict safety procedures. On-site material processing and crushing reduce construction debris efficiently, optimizing recycling and disposal workflows. All operations prioritize structural integrity, worker safety, and environmental protection, following industry best practices. This integrated technical approach enables complex demolition projects to be completed reliably, on schedule, and in accordance with stringent engineering and safety standards. The aquadome on Icon of the Seas spans decks 14 to 20, forming a full geodesic structure with a total surface area exceeding 300 square meters, over half of which is glass, with the remainder aluminum panels. Constructed from 12 individual steel, glass, and aluminum modules, assembly took 8 months. Modules were prefabricated off-site, allowing simultaneous construction of the forward ship section. A specialized spreader frame, supported by 12 crane cables, was designed to lift the entire dome safely. 54 attachment cables connect the dome to the spreader, with wind monitoring critical during the lift. The final installation required precise alignment, pushing crane engineering and operational limits. The Aquadome integrates the largest aqua theater ever built, along with dining and bar areas. This complex installation exemplifies advanced engineering, collaborative design, and precision execution in modern cruise ship construction. The third Bosphorus Bridge, also known as the Yavuz Sultan Selim Bridge, spans the Bosphorus Strait near the Black Sea entrance, connecting Europe and Asia. Its monumental pylons, triangular in cross-section with 1.5-meter thick walls, were constructed using advanced slip-forming technology. The process began with precise assembly of the slip-form system, designed to ensure uniform concrete placement and structural integrity throughout the pylon's full height. Continuous monitoring of form alignment, concrete consistency, and curing conditions allowed for highly controlled, uninterrupted pouring. The slip form moved steadily upwards, enabling a seamless, monolithic structure with minimal construction joints. Safety systems and scaffolding integrated into the slip form ensured worker access and operational efficiency throughout the build. The performance of the slip-forming technique was critical, as it allowed for rapid, precise erection of these massive pylons under challenging environmental conditions, including high winds and temperature variations. This method significantly reduced construction time while maintaining high-quality standards. The successful completion of the pylons exemplifies innovative engineering, precision concrete placement, and advanced construction technology, forming a key component of one of the world's longest cable-stayed bridges. Merdeka 118 in Kuala Lumpur, standing 678.9 meters with 118 stories, is now the world's second tallest building. VSL was tasked with lifting the spire, providing design, engineering, and operation of a specialized heavy lifting system. The spire was divided into modules for staged lifting over 2 years. Each lift used VSL strand lifting units, comprising a central hydraulic jack, upper movable anchorage, and lower fixed anchorage. The system allowed precise incremental lifting, with grippers automatically engaging and releasing strands to hold loads securely. Lateral guides at 3 levels maintained verticality during each lift. The first module was raised 12.8 meters, followed by 12 lifts of 4.3 meters each. Lifting speed averaged 20 centimeters per minute, with loads of 51 to 57 tons per jack. Once the spire reached its final position at 616.9 meters, weight was transferred to permanent anchorage and secured. The operation demonstrates advanced engineering, precise load control, and heavy lifting expertise on a megatall skyscraper. The Maxtruder foundation pile formwork and production system enables precise and efficient manufacturing of precast concrete foundation piles. This advanced technology produces robust piles with a wide range of cross-sections and lengths, suitable for residential, commercial, and industrial structures. The modular system allows customization of automation levels and pile design, optimizing production for project requirements. Prefabricated piles offer significant construction advantages. No excavation is needed, allowing piles to be driven directly into the ground, reducing time and cost while maintaining a clean site. Installation is rapid, typically completed in minutes, and is compatible with various soil conditions, ensuring a stable foundation almost anywhere. Fully cured in the factory, the piles provide immediate load-bearing capacity, preventing settlement and guaranteeing long-term structural integrity, reliability, and safety. A 15 million-liter water reservoir takes shape as precast panels are delivered just in time. Cranes lift panels directly from trucks, while columns and beams arrive simultaneously. Each pre-stressed panel is carefully installed and braced, then post-tensioned on site. In just 9 days, all structural elements are hoisted and securely in place,